cross product. It's something which exists only in three-dimensional space. We don't have analogy of a cross product for the n dimensions. If you were hoping for that, that's like a, I'm sorry, but that's how the things are. Cross product is it's specifically attached to the three dimensions. I mean, even two dimensions not really much suitable here. Three dimensions where the cross product lives, yet it has lots of interesting applications. That's why we have to know it. So symbolically, we write the cross product like this. We put a cross in between the vectors rather than the dot. And conceptually, there's a difference with the dot product because the cross product is something which is a vector. The dot product was a number. This is a vector. Now, the construction of this vector, you can do it in two ways: algebraically, in coordinate sense, or geometrically. In coordinate sense, algebraically, is the easiest to manipulate with. So we start with this. So if you have if you have components of these vectors, a1, a2, a3, b1, b2, b3. If you have components, look how we compute the cross product. I'll open the whole thing and I'll take it through. It looks like a determinant. So you see, in this determinant, the first row is filled with the standard basis vector of my R3 space. The second and the last line, they're just the components of my vectors. Strictly speaking, this is not a determinant, of course, because we never discuss with you what's the determinant when you plug the vectors into the slots of that determinant. So far, we just look at the tables of numbers. There weren't any vectors in there. So this is not a determinant in the formal sense of it, but it's a nice thing to remember because it helps you remembering the formula for how you compute the cross product. Because when you actually do your computation, you do your row decomposition with minus. But this time you don't have any freedom of choosing row or columns. You have to go with the first row all the time. So it's your first row we do the decomposition with, and then the expansion will be, so it's the first term of your expansion, this element I times this minor. This element I times this minor. Next will be negative because we alternate the signs. This element j times this minor. These two little columns. And finally, I think you can expect what will happen next. Finally, you have the last term, which is k vector times this little minor. That's all there is to the computation of the cross product when you know the components of the vector. Here's the example for you. If I have the vector A like this, if I have a vector B like this, it's one of the examples from the lecture notes, I think, but I don't remember which one. All you do computationally, it's very easy. All you do is just build up the determinant, but it's not a determinant in the formal sense, but I hope you realize that. You build a determinant. First row is the standard basis vectors. Second row, the components of the first vector. Last row is the components of the second vector. And you do your decomposition. I won't be opening the decomposition. I'll give you the result right away. It's very easy to check, right? I mean, like this I goes with this minor, and this minor we can just compute it from the top of our heads, right? -1, -3, it's 3, plus 2, 4, it's 7. Then goes j with this minor, these two little columns, and here the determinant is 2 times 3, it's -6. Take another -12, it's -18. That's why plus 18, because j comes with negative. And the little k is this determinant, this minor, which is -4 plus 6, it's 2. And that's all there is to it in terms of the computing the cross product. This is a vector of cross product. You can write this vector in a column form if you want, 7, 18, 2. Either way, I'm happy with it. Any questions in relation to the way we compute the cross product? More interesting stuff comes when you look at the cross product geometrically. And I have this section which is called geometric interpretation of the cross product. And geometrically, this is like so. So on this picture, this is my A vector. This is my B vector. The cross product vector, it will be the vector which, well, it will be this red vector, CA times B. But the formal description of this geometrically sounds like this. Look at this. It says this. The cross product vector, I'll give a name to this vector this time. It will be C vector. It is R3 vector, and it's a vector which has these conditions on it. First, it must be perpendicular to the A. It must be perpendicular to the vector B, and that's what is said here. Perpendicular, perpendicular. Next condition says this. The triple of vectors A, B, and C, it must produce a right-handed triple. And the other condition is the length of the C must be this expression, where theta is the angle between your initial A and B vectors. This vector, it's the angle between your A and B vectors, this angle. Out of these three conditions, or four conditions, on your cross product geometrically, I think the most troubling is this one. I'll explain to you what it means, right-handed triple. It means this to you. It means that if you imagine yourself sitting in the tip of this vector, and you're looking down here, if you look down here, if you imagine yourself, you sit here, and you look down, you have to see a turn, or V-turn, of from the first vector to the second one, counterclockwise. That's what you see on this picture. If you look down, the turn is shown by this arrow. It is counterclockwise turn, and in this case, we call the triple right-handed triple. If for instance you're looking at if you were looking at this, for instance, the cross product of B and A in the other order, so B were first and A were second, then the turn from the first to the second will be this way. And then it's no longer true then if you sit here, you will see this turn counterclockwise. You will see this turn clockwise. So in this case, your cross product will be opposite of this vector. It will go down. That will be the cross product in this case. The same length, the same condition of perpendicularity, but the direction now in the other way, because now you have to be here and you have to look up to see this turn from B to A counterclockwise. You have to be aware of this interesting fact about the cross products. The triple and the order in which you write the triple is important. So you sit at the tip of the last vector and you check the turn from the first to the second. There are another descriptions of the right-handedness. I mean, for instance, if you try to look it up on Google or Wikipedia, they also give you another test when you use your right hand with the first three fingers, and you have to be, this finger must represent the cross product. Which way will be counterclockwise? This way will be counterclockwise. You see, this one I don't remember. I remember the counterclockwise all the time. So the index finger will be the first vector, and the middle finger will be the middle finger with the index on will be the second vector. And your thumb will be the cross product. That's another test, and that's the other reason for the right-handedness. So you make your three fingers, if you don't like my counterclockwise. Index finger is the first vector, middle finger is the second vector, thumb should be the cross product. This expression, by the way, if you don't have any questions, when you look at this expression, does it resemble anything? In your knowledge of your geometry, if you dig your knowledge of geometry, this expression doesn't have any meaning. It's the area of parallelogram based on the vectors A and B. That's the other geometrical, like a byproduct which comes with the cross product. So I have area. This is the area, this product, all together. That's the area of this parallelogram. So another good feature of the cross product, the length of a cross product is the area of the parallelogram based on the vectors A and B. It is something you can use quite effectively. I mean, when you approach the area of this kind of parallelogram, it's not so obvious how to compute that, but with the cross product you can do that, and that's the example for you. It's the one from page 11. It says, look at the two vectors, like this, and find the area of the parallelogram based on these two vectors. If you didn't know cross product, let me call this vector A, this will be vector A, this will be vector B. If you didn't know cross product, how would you approach this question? Well, you can find the length of one vector, you can find the length of the other vector. But the angle in between, that's something you have to think about. How would you approach the angle if you don't know the cross product? What other way to approach the angle between the vectors if you don't know cross product? Dot product, no? because dot product involves cos. So if you don't know the cross product, you have to go via the dot product, which will let you find cos of the angle between the vectors. From that cos, you can find the sine, and then eventually you will find your area of the parallelogram. With the help of the cross product, all you have to do, you have to take the cross product. You have to put the corresponding determinant. You have to find the values of the components now, and that's the values of my components. Look at this. My vector will have the components 24, right? It's this minor. 3 times 7, 21, plus another 3, 24. Negative 13, this is this minor. This is 2 times 7, and take 1, 14, yeah, 14, it's 13. And the last component is 9, which is this little minor. It's 6 plus 3, it's 9. Yeah, so all good. And all you have to do now, if you go after the area, you have to compute the length of that vector, which we know is the sum of the square of the coordinates. I didn't make an effort to compute this rather large number, so I left it for you. If you have a calculator, you can help me with the value for that. If you don't have a calculator with you, which I doubt highly, then you can probably finish it yourself. I mean, all you have to do, you have to find this number and put it in here. And that will be the area of that parallelogram. So in this regard, cross product make a huge shortcut for you in comparison, for instance, if you approach this problem with the help of a dot product.